and Lowry theory. In the year 1923, Johannes Nicolaus Bronsted and Thomas Martin Lowry proposed another acid and bases theory. According to their definition, acids are proton donors and bases are proton acceptors.
Acids are substances with a pH lower than 7. We can test for acids using universal indicator solution, or paper, which turns red or orange, all depending on the strength of the acid. Blue litmus paper also turns red in the presence of an acid. An example of an acid that you are likely familiar with is hydrochloric acid. Hydrogen chloride dissolves in water to give hydrochloric acid. Hydrogen chloride will dissociate to give a proton and a chloride ion. The proton is not just released, but it is transferred to another substance. For our example, water accepts the proton to form a hydronium ion. A hydronium ion is also known as an oxonium ion. A Bronsted-Lowry acid is a substance that releases or donates protons in solution, in our case, hydrogen chloride. A Bronsted-Lowry base is a substance that accepts protons. Lowry theory involves the transfer of a proton from one substance to another. In the introduction, we mentioned that ammonia acts as a base even though it does not release hydroxide ions, which is stipulated in the Arrhenius theory. When ammonia dissolves in water, it accepts a proton from water. Notice that this reaction also involves a proton transfer. Can you figure out which substance is acting as an acid in this example? Which is acting as a base? Please pause the lesson to think about this and resume when you are ready. In this example, water acts as a Bronsted-Lowry acid because it releases a proton. Ammonia acts as a Bronsted-Lowry base because it accepts a proton. So a base, according to the Bronsted-Lowry theory, does not need to have a pH greater than 7, or turn red litmus paper blue, or turn universal indicator solution or paper blue or purple. The only requirement is that it is able to accept protons. Have you noticed that water acted as a base in our first example, but as an acid in the second example? Substances that can act as either an acid or a base are amphoteric. In conclusion, according to the Bronsted-Lowry theory, an acid is a substance that dissociates to release or donate protons. A Bronsted-Lowry base is a substance that accepts protons. Therefore, an acid-base reaction, according to this theory, involves the transfer of a proton.
Acid and base and crystallizing. All acids dissociate in water solution to produce hydronium ions. They obey the Bronsted-Lowry definition of acid, since they donate a proton to a water molecule. Group 1 and Group 2 hydroxides dissociate in water solution to produce hydroxide ions. Hydroxide ions are Bronsted bases, since they can accept a proton to form a water molecule. The ammonia molecule is a Bronsted base too. In water solution, it accepts a proton from a water molecule to form an ammonium ion. The reaction of hydrogen chloride and ammonia in the gas phase involves transfer of a proton. Hydrogen chloride is the donor of the proton, and ammonia is its acceptor. Thus, hydrogen chloride is the acid, and ammonia is the base, in terms of the Bronsted-Lowry theory. This theory explains why neutralization reactions can occur also in the absence of water. The reaction of ammonia and water is reversible. This means that the ammonium ion can donate a proton, which is in turn accepted by the hydroxide anion. In the reverse reaction, the ammonium ion is the acid and the hydroxide ion is the base. Ammonia and ammonium ions are called a conjugate pair of base and acid. Similarly, water molecules and hydroxide anions form another conjugate pair of acid and base. Therefore, we have two conjugate acid-base pairs in this reaction: ammonium ions and ammonia molecules, and the other one, water molecules and hydroxide anions. The dissociation of ethanoic acid involves the formation of two conjugate acid-base pairs too. Ethanoic acid donates a proton, changing it into a conjugate base, the ethanoate anion. The water molecule accepts a proton, acting as a base, and transforms it into the conjugate acid, the hydronium ion. According to the Bronsted-Lowry theory, each acid-base reaction involves the formation of a new acid-base pair, conjugate with a reacting pair of acid and base. The components of a conjugate pair of acid and base differ by only one proton. The acid has one proton more than the conjugate base. Notice that water is not just the medium in which the dissociation of acids and bases takes place. It takes an active part in acid-base reactions. In the presence of bases, water behaves as an acid, and in the presence of acids, as a base.
The reaction of gaseous ammonia with gaseous hydrogen chloride is an example of an acid-base reaction that takes place in the gas phase. Ammonia as a base accepts the proton donated by the acid, hydrogen chloride. The reaction products are ammonium ions, the acid conjugate to ammonia, and chloride ions, the base conjugate to hydrogen chloride.